The final video in Riemann sums is going to cover the right Riemann sum with 5 intervals on a unique set of bounds from 3 to 6 on a different function 2x. So now in this function, you should be able to actually draw this and go from, let's see here, we're going to start at 0, 0, and because it's the function y equals 2x, again it's f of x equals 2x, we should be going up to 1, 2, over 1, up to over 1. So we should be able to see this function relatively clearly on how it behaves. Now, the other piece that's important is we're only actually going to look at the values from 3 to 6. So if I were to do that, I would actually be further out here, playing with this point and going over. Now, it looks like then if I were to do that, my region would look something closer to this. 1, 2, 3. We'd be somewhere way out here. It would be going up as a slant. And then we'd be at the value of my final location is supposed to be 6. 3, 4, 5, 6. So somewhere about here. So this space right in here, I want to find the area under the curve. Now you'll notice in this particular example, that right there is actually what we call a trapezoid. Now there's a way to efficiently find the area of a trapezoid, and I will write it down. The area of a trapezoid, and I actually write out this little symbol here for the trapezoid. The area of a trapezoid is base 1 plus base 2 divided by 2 multiplied by the height. Now this can be rearranged so that you actually identify it as h1 plus h2 divided by 2 times the base. Okay, it just depends on how you see it. I'll notice that this can be represented as a height 1 and a height 2, and then the base is going to be the length of this distance right here, and we divide that information by 2. So this is the actual area of a trapezoid that we will come back to. But I want to use a right Riemann sum with 5 intervals. So I want r sub 5 to be able to approximate the integral from 3 to 6 of 2x dx. Okay, I want to approximate that. So that means that I need 5 intervals. Okay, well I'm going to start off with finding my delta x, which is, again, remember, b minus a divided by n. b is 6, a is 3, n is the number of intervals I'm playing with, which is 5. So that's 6 minus 3, which is 3, divided by 5. So this right here is my delta x. Now that's an uncomfortable looking delta x. Do not overcomplicate this information. Now, again, we've seen the space that we're trying to find the area under. We're, again, trying to cut this into a certain number of rectangles as we find the area of that. We don't need to actually see this graph to be able to do this. Just like we did with the midpoint rule, I'm going to go ahead and start at 3. What I'm going to do with this, however, is I'm going to go ahead and simply add my delta x to that value. Well, to make this as easy as possible, let me go ahead and just convert this to be 15 over 5. The reason I do this is so that my denominators are actually going to be the same, and this will be very easy to add. So this is 15 over 5. If I add 3/5 to it, I will get 18 over 5. I'm going to continue to add 3/5 until I get to the value of 6. So if I add 3/5 again, that's going to give me 21 over 5. If I add 3/5 again, it's going to be 24 over 5, 27 over 5, and then 30 over 5. Now, you'll notice I have 1, 2, 3, 4, 5 spaces. There being 5 spaces there, this is going to be my value of 6. Okay, so again, there's my value of 3, there's my value of 6. These are the values I'm actually going to work with in the middle, just by simply taking this delta x and adding it in. These are the bounds of my rectangles that I'm going to create in this image over here. I'm just not going to do it over here because it's too much work for me. Now, to easily do this, I'm going to go ahead and simply identify that every section I need to find an area. So area of the first region is going to be nothing more than, if I'm using a right Riemann sum, this is the left side, this is the right side. That's the endpoint that I'm going to play with. So my first rectangle, area 1, is going to be equal to the function value at 18 over 5 times the width of this, which is always 3/5. That's area 1. Area 2 is going to be, well, here's my next region, and again, I'm going to look for the height at a certain point. The height is on the right side, so 21 over 5. So I'm looking at f of 21 over 5. times, once again, delta x, 3/5. I'm going to do this 5 times, which means I'm going to select this interval, this endpoint, this endpoint, this endpoint, and this endpoint. Therefore, r sub 5 will be nothing more than f of 18 over 5, but the function f is 2 times x. So I'm going to have, very carefully, 2 times 18 over 5, that's f of 18 over 5, times 3/5. That is the area of the first rectangle. Plus, I'm now going to plug in 21 over 5 to this function. I'm going to have 2 times 21 over 5 times 3/5. And again, the 3/5 is coming from the fact that I'm multiplying it by delta x. The width times the height. The width, 3/5, times the height, f of 29 over 5. And f being this function, that's the height of the function. So I'm going to have, again, 3 more of these. 2 times, looks like 24 over 5, times 3/5, that's 5, plus 2 times, looks like 27 over 5 as my next one, times 3/5. I have to put that bracket there and there. And then finally, plus 2 times 30 over 5 times 3/5. Keeping in mind that the 2 in every single one of these is because of the function f of x being 2x. Again, in the last examples we did x squared. In this example we're doing 2 times x. Keep in mind these examples can get more and more complicated as we go. This can all be simplified hopefully efficiently, knowing that all of these are going to be divided by 25. I can factor all that out. All these are going to be multiplied by 2. I can factor all those out. And then I can manipulate with the basic numbers. So if I do this very carefully, the 2, the 3, the 5, and the denominator of 5 can all be factored out, giving me r sub 5 equals to 2 times 3/5, which is 6 over 5, but then another 25, multiplied by, all that's going to be left is 18 plus 21 plus 24 plus 27 plus 30. And again, this would probably be the most efficient way to simplify these values. Again, the 6 over 25 is coming from 5 times 5 times 3 times 2, 5 times 5, and then 3 times 2, 5 times 5, and then 3 times 2, and so on and so forth. So this will provide us with a very smooth, efficient way to approximate that value. Now when we do this, the question is this an over or an underestimate of this example? Well, since we're using the right Riemann sums, if I were to pick any one of the values to the right here, draw an area up, and then cut it across, notice it's going to be an overestimate if we were to ask. And that covers Riemann sums.